Assalamu alaikum warahmatullah. So, um, this is your first lecture on linear algebra. Sorry for the delay. I was supposed to post the video a bit earlier, so I couldn't because of some other tasks. Okay, so um, so the first lecture is called as um, the essence of linear algebra. So first the question comes that why do you use a linear algebra, right? So in the introductory class I actually told you that um, linear algebra is used in different research domains like machine learning, deep learning, data science, right? So in those domains, what do you use? What is the use of this linear algebra? Okay. So the use of linear algebra is basically um, to solve to solve um, linear system of equations. Okay. Equations. So um, you know about linear equations, right? Let's say you have two linear systems of equation like 2x plus 3y equals to 5, 5x plus 4y equals to, let's say, 14. So this is a linear system of equation with two unknowns. Okay, so this is easy to solve, but um, what about a bigger linear system of equations um, like let's say um, 1,000 equations with 1,000 unknowns. So in those cases the solutions become really complex. Okay, so in those cases linear algebra is very fruitful to um, or is very effective to solve the equations. All right, now to um, to start the um, formally uh, on linear algebra, the first thing you need to know is vector. So what is a vector? Okay, so vector is basically the rudiment of linear algebra. Okay, so you have heard about vectors in your previous courses of education, maybe in your HSC or in your A levels. Okay, so uh, a vector can be described from three perspectives. Okay, um, one from the physics perspective, one from the mathematics perspective, and one from the computer science perspective. Okay, so for the time being, we are interested in um, working with vector from the math and CS perspective. Okay, so whenever I say the word vector, I want you to think about an arrow in a coordinate system that starts from the origin. Okay, for for this course at least. Okay, so let's say you have a 2D coordinate system. So let's say this is the x-axis and this is the y-axis. Okay, so so this is, let's say this is a vector. Okay, so this is an arrow. As I said, that whenever I say the word vector, I want to think about an arrow in a coordinate system that starts from the origin. So it starts from the origin and it's an arrow. Okay, let's say um, a pair of number from the math perspective, a pair of number actually gives you one vector. Let's say this, for this vector, that particular pair of number is, let's say, minus 2, 3. Okay. So if you use the basis vector, we know about basis later, but I think you already know this, that if you use the basis vector, then this should be minus 2 I cap plus 3 j cap. Okay. So in this case, these two numbers, or the coordinates of a vector, basically tells you like how to get to it. Okay. So for example, let's say this is your 2D coordinate system and you have a vector minus 2, 3. So it tells you that you should go to the leftward direction of x 2 units, and you should go to the upward direction of y 3 units. Okay, then from the origin to the tip of that vector you would get the desired vector, which in this case is this part that I have just circled. Okay, so for 3D, you add another axis with this. Let's say that particular axis is called the z axis. Okay, so in that case, so with these two axis, there is an additional axis. Let's say this is the z axis, x, y, and z. And for any particular vector, let's say in this case there would be 3 coordinates. So for the previous case we had only 2 parts, as this was a 2D coordinate system. So for 3D we would have 3 parts here. Let's say one particular vector in this case is 2, a negative 1, and a 3. Okay, so let's say 2, negative 1, and a 3. So let's say this is our vector 2, a negative 1, and a 3. Okay, so I think you already know these things. It's just a flashback towards your memory lane. Now every topic in linear algebra is gonna centered around 2 operations, or like most of the operations in linear algebra would be centered around 2 operations. Okay, so the first one is vector addition, and the second one is vector multiplication by scalars or by numbers. Okay, numbers that are not vectors. Okay, now what is vector addition? So let's say you have 2 vectors v and w, and you want to add those. Okay, so let's say you have a 2D coordinate system, and this is your vector v, which is 2, 2. And you have another vector, let's say this is 3, negative 3. Okay, so how do we actually add these 2 vectors? So adding 2 vectors is basically if you go to the tip of one vector and add another vector, the other vector here. Okay, for example, if you choose the tip of the w vector and draw um, v vector from here, let's say this is your v vector, then from the origin to the tip of the other vector is, or the tip of the other vector is the resultant vector. For the same case, like from the same approach, if you take the tip of the v vector and draw this w vector there, it might end up here. So this would be from the origin to the tip of the drawn vector is the resultant vector. Okay. So this is the rule of vector addition. We can discuss it furthermore in our discussion session if you still do not understand it. And multiplication by the scalars is basically stretching or squeezing one particular vector. For example, let's say you have this vector v, so you want to get 3v. So how do you actually get this vector? So you actually stretch this vector 3 times. Okay, so this is your 3v. Or let's say you want to get minus 0.5v. So this would be let's say it becomes like this. So this is your negative 0.5v. So multiplying by a scalar, multiplying any vector with a scalar to actually stretch or squeeze it is called scaling. Okay, so multiplying this v with this 3 or this negative 0.5 is called the process of scaling. Okay, so in fact every vector that you work with in real life, let's say 3i cap plus 2j cap or any other vector, so these are not vectors, these parts are not vectors. Okay, these are vectors and these are basically scalars. Okay, this is a very small basic, and these are called basis vectors, as you might know. Now why we are actually drawing all these pictures? Why are we doing this geometrically? Because, and throughout the course would be doing these things, or would be drawing pictures of vectors to get a clear understanding. Okay, so doing things or thinking about these vectors geometrically actually gives you a clear understanding of what the operations we are doing. Okay, so now as I was saying at the first part of the lecture, that what is the purpose of using linear algebra. So the purpose of doing linear algebra is to see the pattern inside data. Okay, so like let's say you have data, you have raw data, and if you interpret those data with vectors, let's say you have scattered data all around. Okay, so you do not get any insight from this scattered data, right? So what linear algebra does is it actually rearranges this scattered data into beautiful pattern of data. Okay, so let's say the scattered data becomes this beautiful, it becomes this beautifully rearranged data, or rearranged, yeah, rearranged data is basically information. Okay, so the purpose of linear algebra is to like seeing pattern in data, so that it makes sense to you, so that data actually becomes information. Okay, so you would see at the later part of this course that how do we actually discover pattern among data. Okay, yeah, so that data, that particular data or particular set of data actually makes sense to you. Okay, so now let's go back um, to the basis vectors. So any time that you are scaling two vectors and adding them, it is called the linear combination of vectors. So um, let's say you have two vectors. Okay, so going back to this point, vector addition. So let's say you have two vectors. It's a v and let's say w. Now what you want to do is that you scale these two vectors. Let's say, as I said, that multiplying by a scalar is called the process of scaling. Okay, so you scale these two vectors by multiplying with scalars, and you want to add them, right? So this part, so this operation is called the linear um, or this is a different vector, right? Let's say this vector is, let's say, y. So this y vector is basically linear combination of these two vectors v and w. Now why this is called a linear combination? Okay, so let's say you have these two vectors v and this is v, and let's say this is w. Okay, now if you want to add these two vectors, then as I said, from the tip of the first vector, let's draw the second vector. So this is adding them, adding these two vectors v and w. Now if you fix one of the vectors, let's say you fix the w vector, this vector is fixed, and you let the other vector move freely. Okay, so these vectors become this by, so basically you're scaling these vectors, right? So if you fix one of the vectors and let the other vector move freely, then the resultant vector, as you would see, so this is the resultant vector, right? So this is the resultant vector, this is the resultant vector, this is the resultant vector. As you can see, this resultant vector is or the tip of the resulting vector actually draws a straight line. So this is this would be a straight line. It doesn't look so straight though. Okay, so that's why like scaling and adding two vectors is known as the linear combination of the vectors. Okay, so this is one important terminology that we would be using throughout the course. Okay, so now the question is, in this example, I actually fix one of the vectors and let the other vector move freely. What if I let both of the vectors move freely? Okay, I do not fix any of the vectors and I let all the vectors move freely. So what would be um, my output? So as you can see, if I fix one of the vectors, I could only reach a straight line in this 2D coordinate system, right? So um, my achievement in this whole 2D coordinate system is basically this particular straight line. I cannot move anywhere else from this straight line if I fix one of the vectors. Now, if I do not fix any of the vectors, if I let both the vectors move freely, then what could I achieve? So I think this is very intuitive, that we can achieve every point on this plane, right? So we can reach to any point with particular combination of these two vectors. Yeah, so I can reach to any point, any part of the, I can reach any part of the 2D coordinate system if I let both of the vectors move freely, right? So I reach every possible point on this plane, or I can say I can get the whole plane, right, with particular combinations or particular linear combinations of the two vectors, right, in a 2D coordinate system. Another possibility is that I can be in the origin if the two vectors are multiplied by 0. So 0 is another scalar. So yeah. So the reason behind explaining this, that I can get the whole plane or I can get only a straight line, is that the set of all possible vectors that you can reach with all the linear combinations of the given vectors is called the span of the vectors. Okay. So what is the span of the vector? Span of the vector is basically the possible vectors that you can reach with the vectors that you have in your hand. Okay. So for this particular example, if we fix one of the vectors, we can only get one straight line, right? So the span of these two vectors in this case is the straight line. That is the span. So that particular straight line might have an equation, let's say 2x plus 3y equals to, let's say, 5. Okay, maybe it is incorrect, but I just gave you an idea. Now, if I do not fix any of the vectors and let both of the vectors move freely, then the span of the vector is basically the 2D plane, right? Because I can reach any point with the help of these two vectors, with the linear combination of these two vectors, right? Okay. So what happens in 3D space? We have worked with 2D space. What happens with 3D space? So in 3D space, to get any point on that 3D space, you need 3 particular vectors, and you have to let all the vectors move freely in that 3D space. So only then you can get the whole 3D space with the linear combinations of 3 vectors. Okay. So you have take one homework, that one homework would be watch the first 3 videos of 3 blue, 1 brown. I actually um, told you about this. Sorry, I actually told you about this channel, YouTube channel, in your discussion session, first discussion session. So if you go to 3 blue 1 brown and just search for the essence of linear algebra, the essence of linear algebra. So it is very difficult to actually draw all these things on a static plane. So in this channel or in this playlist, you can see the visual interpretation of all these operations. Okay, so that would be better for you to understand. So this was the first phase where you get to know what is linear combination. So now we'll be talking about an idea that is called the linear transformation. The linear transformation. What is linear transformation? So linear transformation. So transformation is basically a fancy word um, used for function. Okay. So both words have same meaning. Function. Okay. So what is the work or what is the task of a function? So the task of a function is basically transforming like anything into something else. Okay. Let's say you have a function f of x and you input numbers there. Let's say 5, 2, 7. Okay. And what this function does is it actually squares that particular number. Okay. So let's say 5 becomes 25, 2 becomes 4, 7 becomes 49. Okay. So yeah. So in function you actually input something and you get output of a similar genre of thing. Okay. So you input numbers and you get numbers, but in a transformed version. Okay. So in case of linear algebra, the transformation function actually changes the vectors or the basis of the vectors. So if you give input of a vector to a particular transformation function or particular transformation, then it becomes to some other vector with some transformed basis. Okay. So why do we use this term called transformation? Why not using function? So transformation actually gives you an idea or it gives you an abstract idea of movement. Okay. Because let's say this is your 2D system and you have an input vector. Let's say this is your input vector and you want to transform this vector into something else. So after going through that particular transformation function, you get the output of this vector. Okay. So let's say this is your output vector. And this movement that happened here, actually tells you about the transformation that happened here. Okay. So transformation, the terminology transformation is used to give you an idea about this movement. Okay, so let's see this with a detailed example. Okay, so before that, let me mention two main conditions for linear transformation. Two main conditions for linear transformation. Okay, assalamu alaikum. Sorry for the interruption. Actually, I had some computer malfunction. Okay. Anyways, so I was talking about the two main conditions for linear transformation. So, the two main conditions here is that um, all lines must remain lines. Okay, so no curve should be an output. No curve should be an output for a line input. Okay, so all lines must remain lines. So this is your first condition, and the second condition is the origin never changes. So the origin actually remains the same. Okay, so as I said, linear transformation is a process that actually changes the basis. Okay, so one particular example is, consider this vector. Consider this vector. Which vector? Let's say this one, v equals to -1 and 2. So this vector is basically minus 1 I cap plus 2 j cap. Okay, so if I draw this vector, so it is -1, let's say this is 2, so this is the vector. Okay, so this is your vector v. Now by some transformation, so these are the bases, right? So this is your basis vector I cap, and this is j cap. Okay, because this is the x and this is the y axis. Now after transforming, let's say the origin stays the same. Okay, the origin stays the same here. So this was your previous vector v, this is v, and the transformed I cap in this case is, let's say, this one, which is another vector. Let's say this vector is -1 -2, and so this is your transformed I cap, let's say I cap prime, and this is your transformed j cap. J cap prime. Okay, and this is, let's say this is 3 0. Now what should be the picture of this particular vector if the bases are changed like this? Okay, so you'd have the same linear combination, -1 for I cap and 2 for j cap. So if we go for negative um, negative 1 into this particular transformed I cap, then we will get a vector like this, and for this the twice of the transformed 3 0. So we will have a picture like this. So the transformed vector would be this. Okay. So this is a transformed vector. Let's say this is V prime. Okay. So this is some sort of rotation where this I cap actually rotates and comes here, and this J cap rotates and comes here after some scaling done on these vectors. Okay. So what should be the value of this transform vector? So as I said, it will have the same linear combination -1 and 2 with some scaling or transformation done on the basis, right? So the transformed V cap would be -1 into the transformed I cap plus 2 into the transformed J cap, which in this case is -1 into this one, 1 minus 2 plus 2 into this one, 3 0, right? So the vector would be -1 into 2 plus 6 0, right? I've just multiplied it, and the result would be 5 2. So this is the resultant vector. Okay. So for more general formula, so this is a transformed basis. So for more general formula, if you have any vector xy and you transform it in this transformed coordinate system, you'll have a result, or you'll have the resultant vector of x into 1 minus 2 plus y into 3 0. So it should be x plus 3y minus 2x plus 0 y, let's say. So this should be a transform vector for this particular transform 2D system. Okay. So as you could see, for a transformation, if you only know where this basis vector falls after a certain transformation, you'll get to know where any particular or what any particular vector becomes. Okay. Or what should be the transformed picture of any particular vector if you know where the transformed I cap and j cap falls. Okay. So in this way, like, I give you any vector and you can tell like where the transform vector land. Okay. If you only know the picture of transformed basis vectors. Okay. Okay, let me erase all this. Now, in 2D linear system, So what we saw in the previous example, that if you only know where the transformed basis vector lands, so you have to have this information. Okay, in case of the previous example, the transformed I cap actually landed on a particular point 1 minus 2, and j cap landed on a particular point 3 0, right? So what I'm trying to say here is that in a 2D linear transformation, the whole transformation can be described by just 4 numbers, and those 4 numbers are this, right? So if you combine these 4 numbers, 1 minus 2 and 3 0, this becomes actually 2 by 2 matrix, right? Where the first column actually tells you that where the I cap lands, and the second column tells you so these are 2 columns, and the second column tells you where the j cap lands, right? So if you are given a 2 by 2 matrix describing a linear transformation and a specific vector, you can find out where that where the linear transformation takes that vector. Okay, so this is the basic functionality of a matrix. So all the things that we have learned from our high school levels about matrix is vague, because the main functionality of a matrix is to describe a linear transformation for a vector. Okay, okay. So as I was saying, if you are given a 2 by 2 matrix describing a linear transformation and a specific vector, and you want to know where the linear transformation takes that vector, so just take the coordinates of the vector, multiply them with the columns of the matrix, then add together, and you will get the transform vector. For example, let's say you have a matrix 3 minus 2 and 2 1. So if I want to ask you that what information do you get from this particular matrix, so the answer would be this particular matrix is a tool for linear transformation where the first basis vector, that means the I cap, actually lands on 3 minus 2 after the transformation, and the j cap, that means the second basis vector, actually lands on a point 2 1 after the transformation. Okay, so this is the main functionality, as I was saying. So matrices are basically tools for linear transformation, where the columns actually describes where the basis vector would fall, or where the basis vectors would land. Okay, so let's say you have a matrix like this, and you want to know, after multiplying or after the transformation through this matrix, where this vector 5 7 would fall or would land. So what you need to do is take the coordinates and multiply with the columns of the matrix. 3 minus 2 plus 7, 2 minus 1. So the transformed vector would be this, right? So this is basically, okay. Yeah. So this matrix is basically the transformation. This vector is your vector V, and this is the transformed vector. Okay. So for general case, you have 4 numbers in a matrix A, B, C, D. You multiply with a particular vector x, y, right? So the transformed vector would be x into AC plus y into BD. So the resultant vector would be AX plus BY and CX plus DY. Okay. So let me again repeat this because this is very important. So the first column actually specify that where the first basis vector lands, and the second column specifies where the second basis vector lands, right? Let us practice some fun linear transformation. Okay. Let's say you have your basis vectors, let's say you have your normal coordinate system. Okay, this is x, this is y, let's say this is I cap, this is j cap, and you have a transformation. Let's say this transformation is 90 this okay. So let's draw the picture first. So after transforming, the basis vectors change, and you get a picture like this. So j cap comes here, I cap goes there. Okay, so this becomes your new I cap, this becomes your new j cap. Okay, and so this is your 90-degree counter, sorry, this is your 90-degree counter clockwise rotation, right? This is your 90-degree counterclockwise rotation. And so what should be in the normal case here, the vector or the matrix is 1 0 0 1, because this is the identity matrix. If you multiply any vector with this matrix, it doesn't change. It doesn't change means the basis actually stays the same. Okay, and after coming here, the I cap becomes 0 positive 1, and the j cap becomes negative 1 and 0, right? So the matrix for doing or performing a 90-degree counterclockwise rotation would be 0, 1, which comes from here, and -1, 0. Right? So this is your 90-degree counterclockwise rotation. This is your first operation. Let's see another operation. Let's say you have your normal basis vectors, and after transforming, the I cap remains the same, but the j cap again sorry sorry, I again had some complications with my machine. So yeah, so what I was saying is that for okay, let's draw it again. I'll just take some few more minutes. So this is your, let's say, after transformation, so your I cap stays the same, but the j cap comes here. Okay, so if the I cap stays the same or remains the same, then it should be 1, 0, and this j cap would be 1, 1. Okay, so in this case, the if you multiply any vector, it will be shared, right? So that's why the transformation is called sharing. Okay, so if you want to perform sharing on any particular object or vector, you will have to multiply that vector with this particular matrix, right? So the point established from today's class is that matrices are language to describe linear transformations, right? So every time you see a matrix, you can interpret it as a certain transformation of space, right? So this is the takeaway from the first class, that matrices are not just some blocks of numbers. Okay, matrices are basically tools for linear transformation, which can transform any basis on a particular space. Okay, so please watch the 3 videos of 3 blue 1 brown, as I mentioned. So you'll have a very good visual interpretation of what I just taught in the first class. Okay, and please do make hand notes on this class lecture and post it or submit it. I'll give one demo of how you should make the hand notes based on the class lectures. Okay, so see you in the next discussion session, inshallah. Assalamu alaikum.